Okay, welcome. Welcome to the very last webinar of this entire course. And so today is the goodbye webinar. And next week is the last week of classes, and we only have a few days and then we have a final. So I don't do a webinar next week because this is our last day where we have new material to talk about. So let me tell you the topics that we're going to be covering, and not too many. This is going to be probably the shortest webinar of the class because we don't have that much to do. So I try to lighten up at the end because especially if you're, taking other classes at our college, they tend to get harder at the end. So I'll start out with Q&A. If you have any questions, feel free to pop in the chat box and I'll be happy to answer. And then I'm going to talk about ANOVA, analysis of variance. And that's going to be all about something that we haven't done yet in terms of a hypothesis test. We've talked about, for example, is there a difference between two different quantitative variables? And in terms of their population means, which is, by the way, what you're going to have to do with your project. But we haven't talked about what if you have 3 different variables or 7 different variables or a whole lot? How do you tell if there's any difference or are they all the same? And that's going to be called ANOVA. We'll talk about the requirements to be able to do ANOVA. And it turns out, I'm just going to list them, talk a little bit, but let you know that you really need to take an advanced statistics class to truly understand how to check the requirements. But we'll talk about some. And we'll do some examples too, or one example. And then we'll talk about project 2. And I'll give a little chat about the end of the class and, what's left, because not too much left. So any questions about anything? Any questions? Okay, if there aren't any questions, let me get into ANOVA. So the first thing is it's a little bit confusing in terms of the name. ANOVA actually stands for Analysis of Variance. So it's an acronym. And mathematically, there's a lot of stuff involving variance, but I throw that all under the carpet. We don't touch variance. We don't look, we don't like say, is there something about the variance? That's all kind of the behind the scenes mathematics. So be careful about thinking that analysis of variance is all about variance. It's not. It turns out that it's all about means. So it tests to see if means are all equal or they not all the same. So it turns out H naught is mu1 equals mu2 equals ... equals mu n. So this is something that a lot of people make mistakes on. The opposite or the other side of all the same is not that they're all different. Okay? You could have, let's say we're talking about the average age of people in all 50 states in the United States. And H naught would be that the population mean age for every state in the United States, they're all the same. But for them not to be all the same, it doesn't mean that every state is different from every other state. Because you might have, say, California and Arkansas have the same age. I have no idea, but let's suppose those have the same age. But maybe Nevada had a different age for a population mean age. Then they wouldn't all be the same, even though 2 of them are the same. Does that make sense? So the way to state the alternative hypothesis, what I've learned from practice is that if we do it in symbols, everyone is confused. So I don't do it in symbols. We're going to do it in words. And that is at least 2 of the population means differ from each other. And for examples, we'll talk about what the means are about. Don't just say it in words like this. And also H naught, if it was all the states, that n would be 50. Or let's say you were looking at just looking at the, say, average age of students at the California community colleges, the UC universities, and the Cal State universities. Then you would say mu sub 1 equals mu sub 2 equals mu sub 3, because there's only 3 to look at. Or maybe mu sub CCC equals mu sub UC equals mu sub CSU. So if there's only a few, usually just put subscripts that kind of tell what they are. If there's a whole bunch, we use this dot, dot, dot notation. Any questions at all about what this is about? Okay, so notice again, and this is important, for some reason people do not listen to my webinars, and you have to, because I take off points if you don't listen and you do something different. H naught must be in symbols. H1 must be in words. That's a requirement for the null and alternative hypotheses when you're doing analysis of variance. Okay, so if you have H naught in words, I take off points. If you have H1 in symbols, I take off points. So again, every week we have different stuff. And for ANOVA, it's better to have symbols for H naught, words for H1, so I make it a requirement. Any questions so far? Okay, one thing you might want to think about is, we haven't compared many things. Like, for example, the average age of states in the United States. But we have compared 2 of them. So if we want to find at least 2 of the populations different from each other, why can't we just say test California and Nevada, then test Arkansas and Pennsylvania, then test Alaska and New York, and just do every pair and test them all. And if any of those have a low p-value, then you say, hey, at least 2 of the population means different from each other. Any idea what's wrong with that? Any thoughts? Let's say you were using a 5% level of significance for each of them. Any thoughts? Okay, if you don't have an idea, the idea is if you have to do a 5% level significance, let's suppose they were all the same, but you're going to be testing pairs. And there are hundreds and hundreds and hundreds of different pairs of states in the United States that you'd have to test. And each time you'd have a 5% chance of type 1 error. And if you did that hundreds of times, at least one of them almost certainly is going to have a type 1 error. And then you're always going to do it wrong whenever they're all the same. So that doesn't work. And ANOVA, again, I'm not going to kind of go through the mathematics of ANOVA. That's mathematics and advanced statistics and all that. But you can trust me that ANOVA takes care of those issues. So you can't just use a bunch of tests for a difference between 2 means, try every pair and say you're done. That does not work. All right, so the next thing is think about in the past for other hypothesis tests. We had to have some requirements. So if you remember, there are a bunch of requirements. One, for everything we do in all of statistics, one is no bias. Hopefully you're down with that now. We've talked about that since day 1 of the class. If you have bias, then you have really unreliable hypothesis tests, period. So bias is definitely going to be true. If you have bias, that's bad. So requirement is basically little to no bias at all, okay, which is true of all different hypothesis testing. Okay, so that's going to be 1 for sure, because that's just true of all of them. But there's going to be a whole bunch of others too. But I figured I might as well go through that one because that's the one we know. So let me show you a bunch of others. So 1 is all sampling distributions are approximately normal. So like I said, if you did, the average age of states in the United States, you'd have 50 different sampling distributions, and you have to assume that they're all approximately normal. Now you could do that by getting an unbiased sample of over 30 in each state, but that's a lot of work because you're going to be, needing to survey over 30 for 50 different states, and that is like over 1,500 different people all over the country. and that's a lot of work. So just note that even though, it sounds like an easy requirement, it's actually not an easy requirement. It's a lot of work to get this one right. Okay, so the next one is the population standard deviations must be equal, and it could be approximately equal is good enough. And if they're not, then ANOVA doesn't really work. Okay, if they're really different from each other, then the math doesn't work. So in this class, we are not going to even talk about how you decide if all of the standard deviations are equal to each other. But at least you understand, hopefully, the word standard deviation. So as I mentioned, no bias. So simple random sampling is a way to always get no bias, but there's other ways too. But no bias is the main one. If you have bias, you can't do any hypothesis test. So another one is the samples are independent of each other. Okay, that's usually a pretty easy one because typically you're not going to have a dependent relationship. You're just going to ask, a bunch of people in this group, that group, and the other group. So the samples are independent from each other. But you need it. Okay. And then finally, the samples were consistently taken. So that would be more like, let's say you wanted to find out, instead of heights, average height, let's suppose you wanted to find out about, how much people like Trump in each state of the United States. So you can do samples in each of the states, but it's going to take a long time. And if you went to California, and then you went to Nevada, and then you went to Pennsylvania, and then you went to Alaska, you just went from state to state, it might take months and months and months to do that. And had you gone to, say, New York 5 months ago and asked, 31 people in New York how much they like Trump, and next month you went to, let's say you went to Oregon. Well, the problem is that things have changed 5 months ago to next month because you probably know that Trump was indicted. So there might be a difference because of that, but the samples, because they were taking at different times, they're not consistently taken. Do you see that would be an example of not being consistent? Any questions so far? Any questions? Okay, so these are tough requirements. Okay, they have to be done right, and you got to remember to do them all. We're not going to actually physically do ANOVA, but ANOVA turns out to be done a lot in the research world. So if you're going to go and get a master's, there's very high likelihood you're going to have to do ANOVA for your master's thesis. Just let you know that. And you'll probably have to take another stats class to learn more of the details. Right now, this isn't truly an introduction to ANOVA one day. And in fact, just to let you know, we're only doing something called one-way ANOVA. And as you might guess, there's two-way ANOVA, there's multi-way ANOVA. So there's different kinds of ANOVA. We're just doing one-way ANOVA. So even that isn't the end. Any questions? Okay, so let's do an example. Okay, so here's the example. Let me do this. Suppose that a study was done. When I say suppose, that means I just totally made up these numbers. To analyze the racial differences for the distance in miles that people live from the nearest public library. Might be an interesting thing to study. If you want to get a master's degree, that could be a cool one. The data from the study are shown below. And what we have is white, black, Hispanic, and other races. And just made a table. And as you see, the first person, or this person I asked, said they were white, and they live 15 miles from the nearest public library. Okay, over here, a person was Hispanic and lived 5 miles from the nearest public library. Any questions on reading the table? Okay, notice that here we have 4 different categories: white, black, Hispanic, and other. And we want to see if they all have the population means of the same population means, or is there a difference? So this is a typical ANOVA kind of question. So it's ANOVA because, again, it's definitely 4 different variables. And we have quantitative, not qualitative. And that makes it ANOVA. Okay, but we're going to need a whole bunch of assumptions to make the conditions satisfied. So what assumptions? Let's take a look. We must assume that all 4 distributions of distance from the nearest public library are approximately normally distributed. Well, notice that our sample size for whites were 6, for blacks were 4, for Hispanics were 6, and for others were 4. Each of these sample sizes is definitely not over 30, not even close. So that means all 4 of these have to be assumed to be normal. If we had, say, surveyed 35 whites, but then the blacks, Hispanics, and others were all small sample sizes, we wouldn't have to make the assumption for whites, but we would have to make the assumption for black, Hispanic, and others. Any questions on that? Okay, we have to assume all population standard deviations are equal. That's just pretty much something you're going to assume. You have to assume simple random sampling. There's no bias because here in the statement, it didn't state at all about how the study was done. So we have to make that assumption, which there's a good chance is wrong. The assumptions are bad, but you have to, you have to. Okay, we have to assume that samples are independent. I doubt that's an issue at all, because if you can do a survey asking a bunch of people, what is your race and how far are you from the library? There's no dependency relationship there. You're not asking like a pair of people and then another pair of, like 4 people that are the 4 different races, and then go to another group of 4 people and then another people, where they're all kind of tied together. That would be dependent. So there's a good chance that these are independent anyways. And then finally, we have to assume the samples were consistently taken, especially with a small sample size. There's a good chance that that's true. May not be true, because if you went to a community that was mostly Hispanic, and it was, say, some small town that didn't even have a library, maybe the nearest library from that town was 100 miles away, then you went to another town that was mostly black that did have a library, then you're not consistently taking the survey. Does that make sense? So that would be an example of not consistently taken for this particular type. Okay. So now let us do ANOVA. Let's conduct the ANOVA experiment. Okay, so again, we have white, black, Hispanic, and other. So our H naught is going to be mu sub W, the population mean, distance from the nearest public library for white people, is equal to mu sub B, which is a population mean, distance from the nearest public library for black people, is equal to mu sub H, which is a population mean, distance from the nearest public library for Hispanics, is equal to mu sub O, which is a population mean, distance from the nearest public library for people of other races. Any questions at all on anything so far? Okay, I'm not seeing any questions, but please feel free to ask questions if you have them. Okay, and then H1 is at least 2 races have different population mean distances from the nearest public library. Okay, so notice I didn't just copy and paste at least 2 of the population means differ from each other. You want to state it in the context of what's going on. And that is talking about races and talking about, public library distance. Any questions so far? Okay, the name of the test we're going to use is ANOVA. I know you could guess that because that's all we're doing today. And ANOVA, because we have a quantitative variable, the survey question is, how far do you live from the nearest public library? If you ask me, I would say 2 miles. That's how far I am to the nearest public library. Public regular library. I'm less than 1 mile from the nearest true library, which is our college. But regular public library, for me, it's 2 miles. Okay, notice it's a number. It's a number and not a yes/no question or some qualitative question. And also, we don't have 2 different groups or 1 different group or 1 group. We have 4 different groups. And when you have 4 different quantitative variables and you want to see if they all have the same population means, that's ANOVA. Any questions so far? Okay, let's use a 5% level of significance. Kind of the reason is this is definitely sociology, and pretty much that's what they use in sociology. Okay, you could look at the type 1 and type 2 errors, but we've learned that stuff already. So if you were to do this in detail and depth, like for your projects, you got to talk about type 1 and type 2 errors. You wouldn't just say, 0.05 because of sociology. Okay, so just note that. How do you think we're going to get the test statistic? Any thoughts? How are we going to get the test statistic for this hypothesis test? And the p-value, by the way. So that's always what you need to get for hypothesis testing. How are we going to do that? We want the test statistic and p-value, and here's our data. I don't see you jumping in. Okay, hopefully by now you all know. You go to the calculator. And as I mentioned, this is the very, very last webinar of the entire course. So I put this calculator in order which we do things, and you should all be able to guess which calculator number to use because we're at the end. You should be celebrating right now because we're done. We hit ANOVA. That's our last button to hit for learning. And it says enter the data values separated by commas, then hit calculate, and the F statistic and the p-value will be generated for you. So let's do that. So I'm going to go ahead and look at our numbers. Oops, this one. We have 15, 4, 11. And then we had 9, 3, 2. Then for the blacks, we had 12, 1, 6, 6. Then for Hispanics, 9, 17, 5. 9, 17, 5. And we also had 14, 7, 1. And then for the others, we had 18, 11, 2, 8. So I just type in the numbers separated by commas. And then you leave the rest of them blank. And here, by the way, with this calculator, it only gives you 8 opportunities, which will be enough for like the exam and the homework. But in real life, sometimes you need more, and then you can use my spreadsheet, and there's a lot of other spreadsheet-based things that you can use. Then hit calculate. So a couple things is we have our test statistic. This is called the F distribution. Okay. And our test statistic is F is equal to 0.3339 about. our p-value is 0.8 approximately. Notice that the F distribution is a skewed right distribution, pretty much positive. So you don't have a two-tailed test or anything like that. It's always just one-tailed. And this picture shows you, where the rejection regions are for the most common. We had 0.3339, and notice that that is bigger than actually any of these values here. Okay. And so it's not in the rejection region. Notice here's the F distribution. So if you have a test statistic over here, then the area to the right of that distribution is 0.3339. I'm sorry, is 0.8009, not 0.3. It's this guy. The p-value is the area to the right of the test statistic when we're talking about an F distribution. So let's write this down, 0.3339 and 0.8. All right. By the way, there's actually something really wrong with this particular example. Like in the real world, you should never do what I just did. You know what's wrong? Give you a moment. Looking at the table. But I figure I should say this since we're the last webinar. You really need to understand this because it's a common mistake a lot of people have in the real world. Okay, I don't see jumping in. Okay, what's really wrong with this is the sample size. I mean, for the blacks, we have a sample size of 4. You should never do statistics at a sample size of 4. Okay. For the whites even, and the Hispanics, we had a sample size of 6 each. Still really, really tiny. And this is pretty meaningless. So just a warning, just because I did it as an example, doesn't mean you should ever do this in the real world. The only reason why I kept the numbers real small is so it'd be really fast for me to show you how to type them in. So that's why in the real world, definitely you would ask more than, 6, 4, 6, and 4 different people from each of the groups. That would be ridiculous. So I want to give you that heads up. And our p-value is 0.8, which does not mean that they're all the same. I mean, it might just mean we had a sample size of 4. So good luck having a small p-value. So we have a big p-value, and hopefully by now you know that when you have a big p-value, you fail to reject the null hypothesis, and you have statistically insignificant evidence. So the conclusion, let's write it down. So since p is equal to 0.8, which is definitely greater than 0.05, there is statistically insignificant evidence to make a conclusion that, and the good news is I can copy and paste H1 and change the capitalization, that lowercase, at least, 2 races have different population mean distances from the nearest public library. Okay, so it's insignificant because we have a small p-value. And that's pretty much it. Any questions at all on using ANOVA? It's not the hardest test in terms of for our class. It's much harder in the real world, because especially in the research world, because of all those conditions you have to have, which are really hard to satisfy. But in our class, I just want to make sure you know those conditions are there and be able to state them, and then know how to find the null hypothesis, or write down the null hypothesis in symbols, write down the alternative hypothesis, in words, know the name of the test, ANOVA, be able to put in the calculator to get your test statistic and p-value, and then state your conclusion, which is pretty simple. So that is pretty much it. All of the one-way ANOVA look very similar. I mean, they're not going to all be about race and nearest public library distances, but kind of the same idea in terms of you're going to have a table of values at which you surveyed, a bunch of groups. Okay, not always people. It could be mice versus cats versus dogs versus lions. I don't know. And you're looking at something, heart rate or something. Who knows? But the point is that you're going to have a bunch of groups and you want to find out if the population means are all the same or if at least two are different from each other. And just note, you never end up stating they're all the same. At a big p-value, we do not say that they're all the same. You never accept the null hypothesis. What you say is, we can't say that at least two of the races have different population mean distances from the nearest public library. They might have it, but we don't have evidence to show they do. Any questions at all about ANOVA? Hopefully you agree this is not the hardest. We're not ending on the really hard note. It's just another hypothesis test with the same kind of things to think about. And I mean, it's not exactly the same, but there's a lot of similarities. So what I want to do now is I want to go to the secret word. And the secret word, oh, I can also say, by the way, I guess I should mention this too. There is another way that you'll see it in the research world, and that is there is statistically insignificant evidence to make a conclusion that race is a factor in the distance from the nearest public library. Sometimes you'll see it written that way. I think I should mention that too. And now I'll tell you the secret word. The secret word is thank you. And I want to thank you, especially you all came because you're here. If I had nobody for the whole time, then the webinar wouldn't have worked out because I always want to make sure I at least have an audience of at least one. So thank you for coming. And, thank you for your hard work, for those of you who are putting in a lot of hard work and, making this happen. And hopefully you learned a lot from this class and you kind of appreciate how important statistics is because it really is important. It's used everywhere. So thank you is the secret word. We're not done with the webinar though. We're just done with new material. So what I want to remind you of is what's left. Okay. So some stuff is, easy and obvious. There'll be an assignment on ANOVA. That's the chapter 13 assignment. It's one of the shorter ones. So that's going to have to be done. You are going to have a discussion post assignment, and I promise you, it is the easiest discussion post assignment of the entire quarter. Okay? If you do it and you do it on time and you reply to someone else on time, then you'll almost certainly get 10 out of 10. If you don't do it, you get a 0. If you do it late, I take off points, but do it. It won't take very long at all. Okay. And just make sure that you reply. Okay. And that's important. Okay. And, but yeah, so that's just a note that this is a really easy discussion post assignment. So please do it. It's also an easy secret word test because this is going to be a shorter one. It's going to be less than an hour. So just note that this is kind of one of the easier weeks that way. But we have more to do that isn't easy. So that way was easy. What's due on Sunday? What's the big thing? Besides the chapter 13 assignment and your easy discussion post assignments. Yeah, project 2. Project 2 is a big deal. Okay, it's a decent part of your grade. It's a lot of work. And, it's going to be many pages. Make sure you do that. I want to give you some reminders. Maybe I'll pop into the syllabus. So one is that it is due on June 23rd. Okay. I recommend submitting it by June 22nd. And that way, if you have internet problems or you can't get to the site, you got a whole day to figure it out. Maybe even June 21st. Okay. So again, you wait till the last minute, disasters can happen, and then you lose lots of points because you can't figure out how to do it. And late is a disaster. Often I'll give like 50% off just for being late. So don't be late. If it's very late, you don't get any points. Just let you know. So late is bad. Okay, so early is fine. So that's just a note. And then I do recommend that you email me your rough draft for your project. I will read it if it is sent by 8 a.m. on Thursday. That is California time, by the way. And if it's sent at 8:01 a.m. on Thursday, I won't read it. Okay. Oh, maybe answer some questions if you post in the project to discussion board, but I only read the draft if it's sent by Thursday at 8, same as project 1. And I read it on a first sent, first read basis. So if you send it to me, today, then I'll probably read it tomorrow. Just note. My guess is Wednesday. My plan Wednesday, by the way, I should note, is a holiday. Hopefully you're aware of that. So Wednesday is a holiday. So I'm not even allowed to have office hours on Wednesday. So don't even try to come to my office hour on Wednesday because I can't have them. So I will not be in office hours. I might be a little bit checking my computer, but I think my plan is to do an 18-mile hike with over 3,000 feet elevation gain. I'm not kidding, by the way. I'm a hiker, so I'll probably be spending all day long hiking and off the grid. So Wednesday's a holiday, and I'm taking it off. So just let you know that Wednesday is a day that I probably won't get back to you, but I will be, checking in Thursday. I'll be checking in tomorrow. So definitely those days I'll be around to help out if you post on the project discussion board. I also have my office hours on Thursday and Friday, not on Wednesday. And I don't have office hours tomorrow just because that's not an office hour day. So just note, you can also, pop into office hours, but you can also post in the project to discussion board and get that project done. Make sure you're working with project partners. Remember, if you have no partners and you submit it by yourself, it's pretty much impossible to pass the project. So that is important to make sure you're working with your partners. 3 is best, 2 is allowed. Okay. And the tutors are also available to help. I have a feeling they don't help on Wednesday either because we're supposed to be on vacation. So I don't think they're open. So any day but Wednesday. So that's just a note. Hopefully that'll make sense to you. So just a few notes about the project that a lot of people have make mistakes on. The first is make sure that the focus of the project should be the hypothesis test and the confidence interval. Make sure the order at which you write your hypothesis test stuff is the order at which I told you hypothesis tests should be conducted. That's how you should be writing it up, and that's important. Okay. Note that you're going to use the type 1 and type 2 error ramifications to decide on your level of significance. And that is the ramifications to your client. So you want to really be discussing that. Okay. Also note that you should write down your H0 and H1 in symbols and in words. It's a project, so it means you're doing everything. Also, don't just write it in the quick 1-sentence language that I've kind of shown you to do the assignments on. For the project, you're going to be writing paragraphs. So that's a note. 1 sentence is almost never enough for the main stuff. Okay, so that is important. You should also, when you're done with hypothesis testing thinking, you should reflect on whether the type 1 or type 2 error at that point, after looking at the conclusion of the hypothesis test and your p-value, which one is relevant and how worried should your client be. So that is important. And again, if there's a big worry, that means the probably a larger sample size would be recommended. For the confidence interval, here's what you're not supposed to do that a lot of people make a mistake in. Let's suppose you use 0.05 for your level of significance. Do not say, since I use 0.05 level of significance, I'm going to use a 95% confidence level. They do not go hand in hand. What you want to do is you want to look at the 90%, the 95%, and the 99% confidence intervals. Very easy to switch those numbers, those percents. And then look at the pros and cons of each. Talk about, for the client, which one works the best based on the pros and cons. And then analyze the lower bound and the upper bound individually and talk about the reactions the client is going to make based on the lower bound. Talk about the reactions the client is going to make based on the upper bound. I want to say all this stuff so you're not mad at me when I take off points if you don't do it. And hopefully you all do it and you get great grades. Okay, and you understand it too. Okay, so that's all important. And then let's suppose you decide to use a 90%. If you wanted to use a 99%, how large a sample size would you need if you wanted to use a 99% with the same standard error? And that's going to take a little calculation, okay, using the standard error formula. There's a square root of n in there, just a note. Okay, so that's important. Also, real important is to make sure that you're comparing two quantitative data sets and you're seeing which population mean is bigger. So maybe you're saying they're different from each other. This one's bigger, this one's less. But make sure you're referring to the population mean whenever that's what you're talking about. And you're referring to the sample mean whenever that's what you're talking about. So I'm going through all the mistakes people make, okay, or a lot of mistakes. Okay, very important on the hypothesis tests and confidence intervals. Okay, make sure you refer to the right mean. Okay, you talk a little bit about your sampling that you did. Okay, that's not like many pages or anything. Might be a few sentences. So that's not what the focus is on the project. And convenience sampling is allowed. Just admit to it and say, here are the worries with it. And that's fine. You don't lose points for saying that, for doing that. Okay, if you could do the entire population, then this doesn't work for the project because then you would do that. There's no reason to take a sample and conduct a hypothesis test and find a confidence interval when you could just get the census and know it 100% sure. So that is important. Okay, and then the very last paragraph should be a little summary of the highlights. That's the main stuff. Any questions about the project? Okay, the last thing I want to talk about is what we call the final exam. But I want to let you know that the final exam is only 10% of your grade. It's not a huge part of the grade. So, it's still important, but it's no more important than any of the other exams in terms of your grade. So it is, something you should pay attention to. And there is no extensions on that. You must complete that by Wednesday evening or Wednesday night. And I recommend Tuesday. So if something happens, then you can find a friend, borrow a computer, and make your internet work or whatever. If you wait till the last minute, it doesn't work, you get a 0, period. Don't ask me for extended time. There's no extended time, okay? So that's why I recommend don't wait till the last day. You go to the last day, you ask for extension, I say no, okay? And that's been true pretty much for the whole course. Pretty much on Thursday, I'm going to submit your grades to the college. I'm going to grade your exams on Wednesday, and I'm going to submit it to the college. I'm going to close off the class, and we're done. Don't email me and say, hey, what could I do now? Because that's it. Once Wednesday night is over, the class is over. You can celebrate, have a party. Hopefully you're celebrating how much you learned. But there's no more doing more stuff after the class is over. So that is really important to note, is that Wednesday night, 11:59 p.m. is the very last moment. Anything can be done. And really, that means your exam. Everything else has to be done way before that anyway, by Sunday. Any questions about anything for the course? Questions? I did promise that this was going to be a shorter webinar. And I don't really have anything left that I need to talk about other than thank you for, for your hard work and for coming, and especially those who come to the webinars. That's wonderful. And hopefully you use this stuff for your continued degree or your career, or maybe your investment strategies, whatever it might be. And you understand now how to use statistics to make things happen and do right things. So thank you very much. I am going to call it a webinar. We're done. So have a wonderful, wonderful summer. I am going to stop the recording. Bye.